Hello, good morning to everybody. My name is Peter. I'm heading here at the Fraunhofer Institute, the group for integrated energy supplies. And in the project Green ICT, I'm responsible for the research field self-powered IoT sensors. And this is the reason why I like to introduce you this topic today. And I will also help you tomorrow with the workshop for this topic. So if you think about self-powered IoT sensor nodes as a little motivation, please think about the Internet of Things. The aim of the Internet of Things is that you connect all kinds of physical and virtual objects to optimize their cooperation. By the year 2030, we will have more than 25 billion IoT devices. And a very important component in the Internet of Things are the sensors. The sensors have the responsibility to gather data. They have to collect all kinds of data because also my colleague Max will need data to train his artificial intelligence. So the data has to be gathered, the data has to be processed and transmitted. And then with that data, there is information generated, and this information is used to control the objects to optimize their collaboration. And in the Internet of Things, as you can imagine, there are a lot of applications which do not have access to the power grid, or even applications which are mobile. And if you think about the power supply, there is no possibility to add a power wire to all these sensors. And it also would make a huge effort to provide batteries for all these thousands of sensors. And this is the reason why the power supply in the Internet of Things is a bottleneck. Because the power supply, either by batteries or by cables, would decrease the revenues, and it would make a lot of application at least economically unfeasible. And here the technology of energy harvesting comes into play. Energy harvesting is using ambient energy like light, heat, or mechanical energy to generate electricity. And this electricity is generated directly at the location where the sensor is mounted. So there's no need to provide a cable to the sensor or to recharge a battery because the energy consumption is directly covered from the ambient. There are a lot of benefits. Of course, you do not need wires for power supply. You have a low installation effort because if you install a sensor, there's no need to provide a cable. There are also no maintenance costs for recharging batteries. We do have a reduction of costs. We have an unlimited standby time because you do not have to recharge the battery. We can even install sensors in inaccessible location where you are not able to access from time to time. Another big advantage of energy harvesting is that energy harvesting systems, generators, typically have a wider temperature range. You might know batteries are only usable between -20 and +60 degrees C, and above and below you cannot work with batteries. And of course, energy harvesting or using ambient energy is of course also much more better for the environment. So, a typical energy harvesting system is built by three important components. On one hand, we have the energy transducer. That might be a solar cell, that might be a thermoelectric generator, which uses heat, or that might be a mechanical generator, which uses mechanical power. Then we have the power management. This is a kind of electronic module which adapts the voltage or current profile of the harvester to your load, to your electronic system. And finally, we have also some kind of energy storage device to store a little bit of the energy, to buffer energy, or to collect energy for a certain amount of time to power then more power-hungry actions. So the challenge in energy harvesting is to collect and make use of even smallest amount of ambient energy to power short actions. Here are 4 examples of self-powered IoT sensor nodes from our recent projects, which I like to introduce right now. The first one is called BlueTech, which is a wireless temperature sensor, which uses a thermoelectric power supply. So we're using thermal gradients on hot or cold objects to generate electricity, and with that electricity we power the complete sensor node. So it runs completely without any batteries, without any wires. It just needs a certain temperature difference. In that case, we need 3 kelvins of temperature difference, and from that 3 Kelvin, we generate 100 microwatts of power, and this 100 microwatts of power is sufficient to power a Bluetooth module and sending data once every second. The second example is our Entras module, which is a GPS tracker with additional sensors like an acceleration sensor, temperature sensor, humidity sensor. And this Entras system has either a communication over LPWAN, or we're using cellular standards like 4G, 3G, or 5G. And also this system is completely powered by ambient energy. We either use a solar cell using light, or we use a thermoelectric generator or mechanical harvester to cover the complete power consumption of this module. The third module is called Viva, which is a vibration sensor. This vibration sensor measures the vibration of every kind of machinery, like a pump, like a motor, like an engine, like a railway train, like a vehicle. And this harvest system is also using the vibration as a power supply. So it uses the vibration and generates electrical power from these vibrations. And this electrical power is used to completely cover the power consumption of the whole sensor node, including the energy for the transmission. And finally, the third example I like to introduce, and which is one of our recent project results, is called Cubo. Cubo is a preload force sensor which we integrated in the washer of a screw connection. So we can measure the tightness of any kind of screw connections during operation. So for example, imagine big screws on overhead cranes, on wind turbines, on railway trains, on bridges, which have to be monitored regularly. And this sensor is transmitting the preload force measurement regularly. So you do not have to be on site to measure or to monitor the screw, but you get the information with the help of a radio signal. And the complete power consumption of this sensor is covered by either a solar cell or a thermoelectric generator. So the system is completely self-powered and runs theoretically until the end of time. Okay. This is all from my side. Do you have any questions so far? Yes?
What kind of battery technology did you use in the screw?
In the screw, we are actually, if we use just a supercapacitor to store the energy for a certain amount of time. For example, this system also works during night with a solar cell. So we use the solar cell during daytime to charge the capacitor, and it sends only every 45 minutes. And the capacitor is sufficiently big enough so that it can also send the data during nighttime, because we have charged the capacitor during daytime. Of course, for the Entras module, we use a lithium-ion battery, which is charged by the harvester from time to time. Yeah.
You also account for weather fluctuations in the case of solar cells, or?
I'm sorry?
Do you account for weather fluctuations, like if it's cloudy for 2 weeks and the sensor or the supercapacitor drains all of its energy and?
So actually we have a prediction algorithm developed in one of our projects where we use the weather data and use the weather data to predict how much energy could get in the next days. And so we charge the capacitor or the battery depending on the weather data. So actually we also record the recent charge data and then do a prediction of the potential power to be harvested in the next upcoming days. But we also actually use weather data, but also for the higher power systems, because for the smaller power systems, this would be too power consuming to really get weather data, record the weather data, analyze the weather data. That would be too much, need too much power. Any more questions? Yes.
I also have a question on the smart stream. If it is installed in the rail system, right, and can it withstand severe climate conditions like during winter time? Is the sensor going to work as
Yes, yes, it will withstand these climate conditions. We have sealed it. It is completely water resistant. You can put it in the water and it will work as well. And the only problem is that on the railway train you have severe accelerations, but that might work as well. So we're presently testing these systems in these conditions.
okay? And for the vibration service of that, do you have current applications, for example, in vehicles, motors, or industrial motors?
It's mainly on roller bearings. So the vibration sensor, the aim of the vibration sensor is to measure the vibration of the roller bearing or of the axle or of the vehicle, because if the roller bearing has a mechanical problem or is worn out, then the vibration of the bearing increase. And so by measuring the vibrations on the roller bearing, you can predict when to use new bearings or when to monitor the bearings also. Yeah. So typical applications are bearings, pumps, motors. We also had applications on railway trains, but also there was the aim actually to monitor the bearings of the railway trains. Any more questions? Yes.
Can you already put a price tag on each of these?
Yes, we can. So, of course, the price of these systems mainly depends on the production quantity. If you produce 5, it's very expensive. If you produce 1 million, it's very cheap. But here on the BlueTech, we are talking about 5 to 10 euros. It also holds also for the Entras, might be a little bit more expensive because we have a 5G module in that one. Viva, the same thing. For the Cubo technology, it's a little bit more expensive, but not due to the electronics, but due to the sensor technology, which is actually a special technology which is developed also on at another Fraunhofer Institute, and there the price might be 100 euros if you produce it at quantities higher than 100,000 pieces. But all the other pieces are just standard electronics. Mainly the most expensive parts are the thermoelectric generator or the piezoelectric material or the solar cell. All other components are standard chip modules from components from off the shelf. Any more questions? Yeah.
These projects was like asked by companies, or it was
Part-wise. These technology platforms were developed in public-funded projects, but then the development was done for customers. But we are mostly or often not allowed to talk about the special customization which we do for industrial partners. So these were all platforms from public-funded projects or where we used own Fraunhofer money, and then we offer these platforms to our partners to make a customization for them, to adapt it regarding the size, regarding the sensor, regarding the communication technologies.
and they pay for that.
I'm sorry?
Do they pay for that?
Yes, they have to. We do not do anything for free. Yes, yeah, they pay.
Once the projects are implemented,
Yeah,
they get a license.
yeah. Actually, either they get either we adapt it for them, and they have to pay for the adaptation, but they also have to pay us royalties because we had the background already available.
Yeah, okay, I see. So for further development, they should contact you in order to, you are going to give them the basics information or the basics research about the topic so that they will further increase or implement the system according to what they need in the industry.
So typically we do the implementation for them, or we do the research for them, and of course the product integration is then done by the company. We do not do products, we just do the research. We develop a prototype, a demonstrator, we produce 5 pieces, 10 pieces, 20 pieces, we deliver it to the customer can test it and say, okay, it's fine for me, give me your circuit diagram, give me the software, I will integrate it in my product. And then he has to pay royalties depending on the sales quantity. Okay, good. Any more questions? If this is not the case, then I have another Peter for you for the next topic.